This workshop session is about using the Sigma W module in GeoStudio 2007. Sigma W, like all the other products in GeoStudio, come with an engineering book which gives the details on the formulations and use of the product. In this workshop session, we are going to generally provide an overview of what is in the Sigma W engineering book, and the main purpose here is to highlight some of the key issues when using Sigma W. So the first question, why do a Sigma W analysis, and what is the purpose of doing a Sigma W analysis? More specifically, the question is, why a stress deformation analysis? Fundamentally, the analysis is about assessing forces acting on structures and on the ground and the resulting deformations. It is the deformations that we are after in large part when we do a Sigma W analysis. The interest is in the deformations under working loads and under the ultimate loading conditions. And the whole type of Sigma analysis boils down to two key words. And these two key words are serviceability and stability. Serviceability. The question that we seek to answer is, will the deformation be small enough for the structure to remain functional for its intended purpose? Or stated another way, will the existing building in this illustration here and the tunnel remain functional when we construct a deep excavation as illustrated in this diagram? When we make this deep excavation, tieback excavation, will it be such that the deformation of the building will not be so high that we can no longer close the windows or the doors, for example? Because if the deformations reach the point where this happens, then the building is no longer functional. The building may not have fallen down, but it is not functional. And so when we construct the deep excavation, we must ensure that the deformation of the building will be small enough such that it can still serve its intended function. The same goes, for example, for a tunnel lining. If the construction of the deep excavation causes the lining in the tunnel to crack and perhaps produce leakage into the tunnel, then the deformations have been too large and the tunnel is no longer serving its intended function, or perhaps cannot serve its intended function because of the leakage or the cracking in the liner. As already noted, the structure may not have totally collapsed, but it is not serving its intended function, and this is what we hope to prevent. We want the deformations to be small enough such that the building and structures can continue to serve their intended function. So the key issue here is serviceability. Will the structure remain serviceable? So serviceability is the main concern, is deformations under working load conditions. On the other hand, we have the issue of stability. The question is, will the forces acting on the structure, the tieback wall, lead to be such that they are not adequate and it leads to total collapse? Related to this, of course, we do not want the total collapse, and so from a design perspective then we talk about margins of safety against total collapse, and the analysis is being done to ensure that sufficient margins of safety are available against a total collapse. Another reason for doing a sigma W analysis is to consider soil structure interaction. It is the relative stiffnesses between structural members and the soil that affect the stresses in the structure and in the soil. For example, if the soil is extremely stiff, it will influence the stresses in the structural members. On the other hand, if the structural members are very stiff relative to the stiffness of the soil, this will affect the stress distribution in the soil. So the stresses are influenced by the interaction between the soil and the structure. And in order to do an appropriate soil structure interaction type of analysis, we need a sigma W type of an approach. We also need to do a sigma W type of an analysis if you are working in terms of limit states design. Limit states design approaches require the consideration of two things, as we have already noted. We have the serviceability limit state, and as already noted in a few slides ago, this is all about making sure the deformations will be tolerable and the structure can continue to serve its intended function. We need sigma W to make the deformation calculations. The second component of limit states design is the ultimate limit state, and this is about stability or margins of safety against collapse. When we, in the context of a limit states design approach, we need to factor the load. We need to use load and resistance factors, and this can be done in GeoStudio. For those of you who are working in the context of the Eurocode and are required to work in terms of limit states design, you may be interested in a document that we have produced, and the title is Using GeoStudio in the Context of the Eurocode. This document is in the Papers of Interest folder and is there for your convenience if you need to work in this context. But the point here is, to work in the context of a limit states design, we must use sigma W type of analyses. When doing a sigma W analysis, it is important to have a clear mental picture as to the objective of the analysis. And most importantly, it is important to decide whether the objective is assessing deformations or whether the objective is assessing stability. The reason this is important is that the requirements for doing the analysis may be very different. For example, when we look at stress distributions in the ground for the purpose of a stability analysis, a linear elastic analysis may be more than adequate. And as you will see later, that doing a linear elastic analysis has some advantages and is generally a simpler type of analysis than when we use more sophisticated constitutive relationships. On the other hand, if the objective is to look at serviceability limit states, that is deformations, then we will in all likelihood need to consider a nonlinear type of constitutive relationship, and to do that we need a nonlinear type of relationship if we want to make a realistic assessment of the settlement. In summary, sigma W is all about doing stress deformation type of analyses. Moving on then to some of the sigma W fundamentals. To begin with, there is the theory of elasticity, that is a stress and strain. Sigma W is based on the fundamentals of the theory of elasticity. There are several different types of constitutive relationships. Sigma W is formulated on the basis of an incremental formulation, which is very important to understand to use sigma W effectively. In many cases, we need to say something about a state of stress in the ground before we come along as civil engineers and build structures or do something on the ground. And as a result, we need to establish the in situ stress state. Sigma W has a special analysis type to establish the stress state in the ground, and then pore pressure response due to stress state changes, which is fundamentally all about a coupled consolidation analysis. You do not have to be an expert in the theory of elasticity, but to use sigma W effectively, it is essential to at least have a rudimentary understanding of the theory of elasticity. If you do not have at least some understanding of stress-strain behavior and the relationship between stress and strain, it is rather difficult to use sigma W. So you should have at least some basic understanding of stress-strain relationships and the theory of elasticity to use sigma W effectively. Here are the two very basic concepts in stress and strain. First of all, the definition of stress. Stress is force divided by area. Force divided by area. So it is a force per unit area. The units of stress are kilonewtons per meter squared, or kilopascals, or pounds per square foot. It is a force per unit area. Strain is a ratio of elongation and length. We have an original length and we have some elongation. And the strain is defined as the change in length divided by the original length. It is important to recognize that the units of strain are dimensionless. It's always meters per meter or centimeters per centimeter or feet per foot. So it is a dimensionless parameter. Sometimes strain is expressed as a percentage, but it is simply the strain multiplied times 100 in order to express it as a percentage, but it is a dimensionless parameter. So stress and strain, the very simple definitions of these two parameters. Here is the constitutive relationship for a general three-dimensional case. We have the strain in the x direction is related to the stress in the x direction, the stress in the y direction, and the stress in the z direction, related by Young's modulus and Poisson's ratio. The strain in the y direction and the strain in the z direction. And then we have the shear strain in the xy plane, the shear strain in the yz plane, and the shear strain in the zx plane. Related to these basic equations are two other equations, and that is the equation for the shear modulus. If Young's modulus and Poisson's ratio are known, then we can compute the shear modulus and also the bulk modulus. The important point to recognize, there are only two, that is two independent variables here. If we know E and Poisson's ratio, then we compute G and the bulk modulus. Or if you know the bulk modulus and you know Poisson's ratio, then you can compute E and G. So in sigma, we will be using predominantly E and Poisson's ratio. The shear modulus is more used in quake W, and occasionally we refer in sigma W to the bulk modulus, but predominantly we use Young's modulus and Poisson's ratio in a sigma W analysis. Sigma W is predominantly based on a two-dimensional plane strain analysis. A plane strain analysis means that the one dimension is much greater than the other two directions. That is, the Z direction is much greater than the other two directions. And as a result, we make the assumption that the strain in the Z direction is 0. So the strain in the Z direction is equal to 0. In addition, by making this assumption, the shear strain in the YZ plane is 0, and the shear strain in the ZX plane is also 0. So for a plane strain analysis, then, we are left with this constitutive relationship written in matrix notation and in terms of stress equal to strain. So in this particular equation, when we write it in matrix notation, we know that the first row of this matrix is multiplied times this vector, gives us sigma x. The second row times this vector gives us the stress in the y direction, and so forth. What is important to realize here is that in a plane strain case, the strain in the Z direction is 0. So this value in the strain vector or strain tensor is set to 0. This, however, does not mean that the stress in the Z direction is 0. So the strain in the Z direction is 0, but the stress is not necessarily equal to 0. So if we take stress Z, we take the third row and multiply it times this vector, we get a non-zero quantity. So plane strain. It simply means that in this constitutive relationship that we make strain Z a 0. By making strain Z 0 a plane strain case, we can go one step further, and that is what is called as the K0 constrained case. We make also strain X equal to 0. This is like an odometer test where we have a ring and soil in a ring. In this particular case, both directions X and Z are 0. And when we make both strain X and strain Z 0, then we get a relationship that is from which we can get the equivalent of K0. So in this particular case, we know that the stress Z is equal to the stress X effective. It becomes equal to Poisson's ratio divided by 1 minus Poisson's ratio times stress in the y direction. Taking the stress y to the other side of the equation, we land up with this ratio here, such that the effective stress in the x or horizontal direction divided by the effective stress in the vertical or y direction is related by this ratio of Poisson's ratio divided by 1 minus Poisson's ratio, which is equivalent to the definition of K0. K0 is defined as the effective horizontal stress divided by the effective vertical stress. We will encounter this When establishing in situ stresses, it is a very useful equation to keep in mind while using sigma W. And it's also very important to remember that K naught only applies to effective stresses, not to total stresses. So we have to be very careful when we talk about the ratio here that we are talking about effective stresses. Another important concept is that of volumetric strain. Volumetric strain is simply the change in volume of an incremental element divided by the original volume, which is defined as strain X, strain Y, plus strain Z. This parameter, volumetric strain, is very important because the pore pressure response is related to the volumetric strain in a saturated soil. So if we can establish the volumetric strain, we relate this to the pore pressure response. Now, the volumetric strain is obviously related to the stiffness of the soil grain structure, and in GeoStudio and in sigma W we use primarily two parameters to describe the stiffness of the soil grain structure. The two parameters are the coefficient of volume change m sub v and Young's modulus. And as we will see as we go along here, that part of the volumetric water content function is described by a slope which is representing the coefficient of volume change m sub v. And when we come to a coupled analysis in session 2, we will need to relate m sub v and Young's modulus in order to do a coupled analysis. There are three main constitutive models in sigma W, that is, stress-strain relationships. We have the linear elastic model, extremely useful in many cases. Then nonlinear models, the prime ones are elastic plastic, Moore Coulomb, and the modified Cam Clay models. And throughout this workshop session we will use these three constitutive relationships and various illustrative analysis examples. In sigma W, it has become necessary to define material properties and categorize them in three different ways. The one way is to describe the material parameters as total stress material parameters. For example, Young's modulus E is total E. This is called a total stress parameter. This category of material properties, total stress parameters, ignores all pore pressures. The whole idea of this category is that we do not want to deal with pore water pressures, and when we assign a material with these parameters to a region, then sigma W assumes that the pore pressure is undefined. The second category is what we call effective drained parameters. The material parameters are effective parameters, for example, E effective. In this category, sigma W considers pore pressure, but there is no change in pore pressure due to loading. This could be the case, for example, in a situation where we have sand or gravel and there is some water at depth, and this is gravel. And we come along and we place some load on the surface. There will be a change in stress, but no change in pore water pressure. We need to, however, know the effective stress in the ground because E is often a function of the stress state. So we need to know the effective stress, but using the effective drained parameters and categories, we can determine the effective stress to get the correct material properties, but there is no change in pore pressure when we use this category group. The third group is what we call effective with pore water pressure change. All the parameters are effective parameters, and we are dealing with effective stresses. And if there is some loading, for example, then the loading could result in pore water pressure changes. So this is in essence a coupled consolidation analysis. And as you note here, the reason for categorizing the material parameters in this way is that it is a mechanism by which sigma W can control and deal with the pore pressure conditions in an analysis. So that is a very brief, short overview of some of the fundamentals inherent in a sigma W type of an analysis.